Excellent. My name is Josh Van Eikeren, and I'm going to present today on chemical structure searching using Lucene.net and Indigo. And just a quick note before we get going. A copy of this presentation, all of the demo code that I'm going to show, all of the necessary support files, Lucene indices, etc. It's all located on GitHub. So if you just go to J. Van Eikeren, Chemical Structure Searching Demo, all of this is available. And I'll actually put this back up at the end as well. Just some quick background about me. I'm currently a CTO and co-founder for a startup called Avea Solutions. We build practice management solutions for the mental health industry. We're actually located in Portland here, although I actually work and live in Bend, Oregon, which is about 3 hours south of here. Formerly, I was a CTO and co-founder of a couple other startups, Intellichem and Blue Reference. Both of those startups focused on information management systems for the pharmaceutical industry. And specifically at Intellichem, we actually created an electronic laboratory notebook that replaced the paper notebooks that scientists would use in the lab. So these scientists would basically record their procedures on paper. These are essentially recipes of how to make a particular compound. And they would record them historically in paper notebooks. The problem is, that's not very searchable. And if you're looking to collaborate, if you're looking to be able to build on what other scientists have done before you, paper doesn't give you a lot of options. But once you have that data electronically, then you can basically use those as starting points. You can collaborate. You don't have to reinvent the wheel. But the key for that is to be able to search. And it's not just text that you need to be able to search. It's also science objects. So these are things like chemical structures, chemical reactions, etc. So this raises the question, what actually is a chemical structure? Fundamentally, it's a representation of the atoms and bonds that actually comprise a molecule. It's comprised of two actual sections. There is a coordinates table. This effectively describes how a molecule is visually laid out. And then there is a connection table, which describes the actual atoms and how they are connected to each other. What types of bonds, single bond, double bonds, stereochemistry, etc. And visually, you visualize a chemical structure basically as a graph. You can see this two-dimensional image here that essentially depicts how the various atoms are connected and laid out in reference to each other. Now, you actually store these file-wise in an open file format called a mol file. It's all ASCII text, and as you can see from the image here, somewhat blurrily, you basically see the coordinates table at the top and the connection table at the bottom. So why is chemical structure searching important? The main reason is because while you may have one actual chemical, that one chemical has a lot of names. Each given chemical has many synonyms. Let's take a common example of Prozac, a well-known antidepressant. It's got an IUPAC name. This is essentially a standardized name based on its structure. And just for kicks, I'll give this a try here. N-methyl-3-phenyl-3,4-trifluoromethyl phenoxypropan-1-amine. Fun times. Also has a number of trade names, such as fluoxetine and Deprex, and it has a number of numerical identifiers. So something like a CAS number, a Beilstein index number, etc. If you look at Prozac on ChemSpider, you'll see that it has over 50 synonyms. So the bottom line is that if you're looking for information on a particular chemical compound, searching by text is not a good way of getting the full result set, because you just have so many synonyms. In contrast, each chemical has a single chemical structure, and you can see here the one for Prozac. So historically, there have been solutions that provide structure searching implementations. That's about where the good news stops. There were no open source solutions. There were, however, proprietary solutions. There were various Oracle data cartridges that you could get, where you would basically store all of your mol files directly in a SQL database, Oracle. And then when you wanted to search for one, the data cartridge would perform the actual searching. It would actually loop through every mol file and basically do an analysis to determine whether it matched your query. As you might imagine, that did not perform very well. and you got fairly mediocre performance. There were also some Unix server implementations, which basically provided for better performance, but everything was separated in a Unix cluster. So there were solutions available, and they all had one thing in common. They were ridiculously expensive. We're talking more than $100K per processor per year. And so if you needed that functionality, you had to pay for it, and then you basically had to pass that cost onto your customer. And so it made selling your solutions that leveraged that technology very difficult. The good news is that times have changed. And now you can basically implement a structure searching solution in .NET thanks to open source libraries. And the example that I'm going to show here can actually be done in less than 400 lines of code. And to do this, we're going to leverage two open source libraries. The first is Lucene.net, which hopefully you saw the previous presentation on. This is an embedded document search platform. It provides superior search performance based on the use of its inverted index. There is a NuGet package for it, Lucene.net. And then the second component that we're going to use is called Indigo. Indigo is open sourced by a company called GGA Software. It's a cheminformatics library, and it allows you to manipulate, analyze, and basically draw chemical structures. It's actually implemented as a C library, and then they've built a set of wrappers for .NET, Java, other platforms that will basically extract out the C library. And for all intents and purposes, it's basically a .NET assembly. When I started building my demo for this presentation, I swore that there was going to be a NuGet package for it. There wasn't, so I threw one together, and it's on NuGet as Indigo.net. So the question is, how are we actually going to search for chemical structures? What approach are we going to use? We're obviously going to use Lucene to perform the actual indexing and searching, and that's fine, but Lucene is a document search engine, and what it primarily searches is text. So the problem we have to solve here is we have to find a way to convert chemical structures into a text-based representation that we can search within Lucene. And that's where Indigo comes in. So how are we going to transform the chemical structures to text? So I'm going to use a text example here, since that's something that most people will understand. Obviously, if you're going to index and search text, you're going to take the text you're going to index, you're going to break it down into tokens, and you then basically index those tokens, and then when you search, you're going to take your input search string, break those down into tokens, and then search on the corresponding query. So for chemical structures, we have to break those chemical structures down into features. And a collection of identified features for a chemical structure is what's referred to as a fingerprint. So this is a fixed list. Indigo basically provides a 467 fixed-length byte array that indicates what features are present within a chemical structure. So the index value within the byte array always refers to the same feature. So it basically analyzes the structure, and it says, does it have this feature? Does it have this feature? Does it have this feature? And so what happens is you get a byte array where if the byte is 0, it doesn't have that feature, and then 1 if it does. So all we actually care about then are the indices of that byte array where those features are identified. Because we only care what features are actually in the molecule. We don't care about what's not. And those indices are simply integers. And integers can easily be transformed into strings. So basically, what you end up doing is indexing those fingerprint feature indice positions, and then you search by taking your input molecules, generating the features for that, and then breaking those down into the same index strings. Now, when you actually go to search, there are 3 principal search types that chemists are interested in. There's an exact match, where you basically say, I have this input structure, and I want to find all instances of that exact input structure. So it turns out you can't just compare mole files. You can have a molecule that is drawn many different ways, different coordinates, completely different layouts. So what you have to do instead is to generate a unique key for each chemical structure. And Indigo can do that. What it actually does is it generates what's called a canonical smile string. And that is simply a string-based representation of the atoms and how they are connected. It's all based on the connection table. The next type of search you want to be able to do is a similarity search. So you have an input structure, and you want to say, find me all of the molecules similar to this one. And in that case, what you want to do is you want to find the overlap of the features of your input molecule, and then how those overlap with the indexed molecule features within the index. Finally, you want to be able to search on the basis of substructure. And so substructures are essentially, it's a subset of a molecule. So you may say, I want to search for this exact subfeature. And so it will go, and so when you perform that search, it basically goes through and it identifies which molecules actually contain that exact substructure. And so then what you're looking for is a complete overlap between the features of your input molecule and the features that are indexed within the index. But it turns out that only generates a potential match list, because to determine if something really is a substructure, you actually have to do an analysis. And so Indigo basically provides that capability. So once you've identified your potential result set for substructure searches, then you can basically use Indigo to confirm that. So I've got a demo of this implementation. I'm not going to go through everything that's in the demo, but all of this code is available. Chemical structure searching demo. It's a Visual Studio solution. We've got 4 libraries. We've got a core library that contains all of the structure indexing and searching functionality. I've got an indexer console, which is just an example console application that shows how to index a directory of mol files. I've got a searcher client. This was fun to go back in time and build a WinForms application that can be used to search an existing index. And then I've got a ASP.NET web application. It's a little more full-featured called Searcher Web App. And that's actually what I will demo in a little bit. So just to quickly go over the core object model, we've got 4 classes. We've got a class that encapsulates the chemical structure and provides methods for generating images of that structure, as well as the fingerprints and the unique key. We've got a structure indexer class that generates the index, and a corresponding searcher class that can be used to search those indices. And that searcher is going to return a list of results, and those results simply indicate the score for the particular search result, since Lucene does provide you relevance, and then the actual chemical structure that corresponds to that search result. So here is an outline of the chemical structure that may or may not be legible, where we basically have the contents of the mol file. We have an optional name. We have the ability to determine if this chemical structure contains a specified substructure. We can generate a bitmap, and we can generate a unique key and fingerprints. Is that readable? Maybe? Yes. All right. So how do we generate fingerprints? Well, just in terms of generating the unique key, we actually use Indigo to generate the canonical smile string. And when it comes to generating fingerprints, we can basically specify a particular fingerprint type to Indigo, whether it's sim for similarity or sub for substructure. And then Indigo returns the byte array. And then all that we do is loop through the positions within the byte array, looking for bytes with a value of 1. And then what we get out of this is a list of integers. And so when it comes to index that, what I'm actually going to do here, I'm going to escape out of this. And let's just go to the actual code here for this. That might be a little more legible. All right, so here's our indexer. This way, this way. All right, so these are the fields that we're going to create within the Lucene index. And what this indexer does is you simply give it a file path to where you want the index to be built, and you open a Lucene index writer, and then you add your chemical structures. And the first thing we do is we're just going to create a Lucene document, and then we're going to add some fields. What we're going to start with are the fields that you want to be able to retrieve later. So these are not fields that you're going to search, but these are fields that you're going to pull back when you get the actual results. And so here, that's just the name and then the actual mol file contents. And then what we're going to do is we're going to add the actual searchable fields. And so we add the exact key for the chemical structure. And then for both the similarity fingerprint and substructure of fingerprints, we're going to take those integer positions and we're just going to add them as the appropriate fields. We add the document to the index writer, and then when you're all done, close it out. And that's it. So then the question is, how do you search that? And for that, we have the chemical structure searcher. And this uses a Lucene index searcher to basically open the index at the specified path. And then you search. And when you search, you're going to provide an input chemical structure. And you're going to specify a search type of either exact, similarity, or substructure. We start by building the Lucene query. And in this case, it's all based on the actual specified search type. For an exact match, we take the input query structure and we generate the unique key. And our query is basically, we're looking for an exact match where we must have that key. For a similarity search, we take the similarity fingerprint positions from the input query structure, and we basically want to do a must query. Sorry, not a must, a should query, because we are looking for a result set that should contain these similarity feature positions. So what's going to happen is you're going to get results that contain maybe all of them or maybe some subset. And the more features that the molecule contains, the higher Lucene is going to rank it. Finally, for substructure, we do a similar query where we basically take the same substructure fingerprint positions, but here we do a must query. Because in this case, for your substructure, we want to ensure that any potential results contain all of the features from that substructure. So once we have our Lucene query, we just pass it off to the Lucene index searcher. We get back a list of top hits, and then we can loop through those, and we basically get what are called score docs. A score doc is basically a pointer to a result within Lucene. And so we're going to actually extract that particular Lucene document based on the pointer. We're going to create a chemical structure search result. And here's where we put in the fields for the name and the mol file. If you remember, we did that in the indexer because now we want to be able to pull those out as the actual results. And then we record the score as well, so we know what the relevance is, relative relevance of the search result. And then finally, if we're doing an exact or similarity search, we just add the results add the result to the list. But if we're doing a substructure search, we have to do an additional check here to make sure that this particular result actually chemically is a substructure. And so to do that, we basically pass it off to Indigo to actually perform that analysis. And then we simply return the results. And what I can do here now is simply demo the Searcher web app, because anytime you can run live code in front of a live studio audience, you basically have to do it. And we are loading. All right, here we go. So this is a fairly simple demo where you can specify a query molecule, and then you can specify your search type, exact, similarity, or substructure, and then you can search. And there are a variety of ways that you can input that particular chemical structure. You can draw it. This is actually a GGA, the same company that open sources Indigo, also open sources a chemical structure drawing package that's built entirely in JavaScript called Catcher. So you could draw a structure here. You can browse for a file. You can paste mol file contents. But the easiest then is to just load a pre-built sample. So we'll go back to our favorite Prozac, import that in. Here we have the visual representation. And then we can do an exact search. And as you might guess, we find one result. In this case, fluoxetine, which is a synonym for Prozac. Then we can do a similarity search. And in this case, we end up with 100 results. And you can see fluoxetine comes up first. That's the highest ranked result. And then you see other chemical structures which are chemically similar. Now, how similar they are depends on what's actually in your index. So I mean, that's the thing with Lucene. I mean, everything is basically relative. to what's actually in the contents of the index. And now we can demo a substructure, and for that I'm going to browse for a file, and we're going to take this particular substructure, which is commonly found in antibiotics, and search for that. You'll notice we get a lot fewer results, only 14. And within the results, you'll see a number of notable antibiotics, fluoxacillin, piperacillin, ampicillin, and of course penicillin. All right, that is the demo. And so just in summary, all right, chemical structure searching is no longer expensive. It's no longer proprietary. You can now build your own custom solution very effectively and in very little time using open source technologies in .NET, including both Lucene and Indigo. And the other thing I should add is the performance is excellent on this as well. Because Lucene's inverted index allows you to perform the actual searches incredibly quickly, the overall performance is excellent. So once again, a copy of this presentation, all the demo code, more mole files than you would ever like in your life. All the Lucene indices are available on GitHub, j.akron/chemical structure searching demo. And I'm not sure how much time we have left, but I'll bet we have time for some questions. Yes?
So how did you go about converting the source data in the chemical structure to something that was able to be searched by the machine? Is there examples that you grew upon to figure out how to structure the data such that the machine was able to process it as well?
So is your question how it's actually done, or sort of how did I come up with this approach?
How did you come up with the approach of transforming one plus
that was actually available in public literature. Someone had published a paper on using Lucene. They were using a different library to generate the actual fingerprints. But with the advent of Indigo, this became significantly easier. So no, I didn't come up with this myself. No, this was based on existing literature. Other questions? Okay. Thank you very much.